Okay, so let me just remind you what to do with this related rates, this word problems. So the main difficulties of this kind of problem is that the word problems. Okay, so let's do some problem here. All right, for example, this let's do this 27. Okay, so that's 27. Okay, so you have a ladder, and just take quickly. Okay, this is you have a ladder. Just later we move to the OneNote 2. Okay, and this only 12 12-foot vertical wall. Okay, and then you have a ladder leaning against the wall. This is ladder, and the length of the ladder is 18. That fixed. Okay. Now the bottom end of the ladder is pulled along the ground away from the wall. So this the end of the ladder is pulled that direction. Okay, with some speed here, 2 feet per second. Okay, so that's the situations. Of course, when you pull this to the right, the the top of the ladder will move down. This moves down, okay, with some speed also. This has speed, this has speed also, okay. So, but the thing is, you notice, you observe that you have a what do you call a triangle here, a right triangle, okay. So the hypotenuse is always 18. 12, not 12. 12 is the length of the wall, the height of the wall. So this 18, and this height is decreasing, but the space is increasing in length. Okay. All right. So that's what you have. Right. So this is the question. Find vertical velocity of the top end when ladder makes an angle 60 with the ground. So when this degrees at some point, 60 degrees. Okay. Find this a vertical drop. So compute this one. Okay. And find the vertical acceleration. So what is this? Oh, okay. So this we just find a vertical accelerations is that you need to find the second derivative. Okay. Let's do this one first. All right. So we move to OneNote. Okay. Have you seen the note? Yeah.
Yes, sir.
All right. Good. All right. So this is the wall, and this is the floor, and um, this is the stair. So this is 18. It's the all right. So this is the picture. these equations. This is moving away from the wall. So that means the height is decreasing. This moves towards the floor. Okay. All right. So what we have here, let's say, so what we have so far is this. So this is 18. Say this is X, this is Y. Okay. And seems that we will need this angle here. Okay. So that's because the question is about the angle. Okay. So what's known is that this uh, moves this way. So X is increasing. Okay. So what is known is given X dt equals to 2 feet per second. And the question is that find dy dt when alpha equals 60 degrees. So that's the questions, right? So somehow you have to find some relation between x, y, alpha, and then this 18. Okay. So let's see. Right. So what's the equation first? So we need to find this uh, relating this one. All right. So, but notice that this is a right triangle. So you can express y axis in terms of trigonometric functions, trigonometric relations, or you can use Pythagorean theorem instead. Okay. So how x, y, alpha, that's 18 hypotenuse. Option one, use trig. Using sine, cosine, or tangent, whatever you like. Or the second option, use Pythagorean theorem. Okay. So okay, let's do the Pythagorean theorem because that's the easiest possible. Okay, because that relates x, y, and it's 18 directly. We can compute as alpha later on. Okay, so use this one. So by uh, Pythagorean theorem is that we have x squared plus y squared equals 18 squared. What is 18 squared? What is the number? Later we compute. Okay. All right. So the question is that what is dy dt? Okay. So let's do ddt. Remember that x is a function of t. Also the y is function of t. So when you take the derivative, what you have the 2x prime, right? So x prime is dx dt plus 2y y prime equals 0. Okay. So now what you have is Okay, let's make observations. We need to compute dy dt, right? So this one. So we have to do, you have to know the data. This is given equals 2, right? We don't know the x and y, not known yet. You have to find based on the informations. The information that we know is that this angle here at certain instance. So at this certain instance, you got to find x and y based on this. All right, so uh, basically you know that x is, let's see, that's 18. So x is the horizontal component. So that's 18 cosine alpha. Y is 18 sine alpha. Is this okay?
Wait, sir, how do you get the formula 2x x final plus 2y final is equal to 0 again?
This implicit differentiations.
Okay.
Okay.
Yeah, that one.
All right. So this works fine. I mean, you know the alpha is 16 degrees, so you can plug into here. Right. So you know all the data. So you can find dy dt or y prime. All right. So when alpha equals 60 degrees, right? So x is, what is x? X is 18 cosine 60. Cosine 60 is, let's see, it's 1/2, right? Okay. So y equals, let's see, 1/2 square root of 3 times 18. So this is, let's see, this is the 9th. There we go. Okay. So from here, you know that dy dt y prime when alpha is 60 degrees is, let's see, what is this? So that is negative from here. Take x over y. Okay. When is this? When is 60 degrees? So this is the data. Okay, so minus 9 over. Okay, so negative. There we go. So negative. It's negative because, well, it's decreasing, right? So this makes sense because you pull this out to the right, so then y moves down, y decreases, right? So, right, decreases by second. And all right, so the picture is really a part of the problem, solving this problem. You got to draw the picture. And there are two kinds of picture here. You have a general picture like this one. There's x, y, alpha, what is moving, what is changing, and also this is the instantaneous picture. Instantaneous picture means that Oh, this is 60 degrees. This is X and Y. This is 18. This is instantaneous picture, while this one is the general picture. Okay, you take the derivative of the from the general picture, you see. Okay, because instantaneous picture, you get everything constant. So if you take away to everything zero, right? So you get nothing from the picture, no information whatsoever. Okay, so that's how you do the this related problems. Solve this one. Picture. Okay, questions?
Sir, sorry, where do you get the minus x over y?
Solve this. Y prime. Oh, sorry. I missed that one. This should be right. Negative, okay, right? So move it here. On the to right hand side, then divide by 2y. You have x prime also. Sorry. Missed the point. This is given. X prime is 2. Okay, so this 18, 9, this 2. Okay, so then I just need to put this one just to make sure that this is instantaneous that we put data. Questions? Okay, so far?
So can I ask,
Sure.
for the hypotenuse, why does it stay 18 whereas the height doesn't stay 12?
Well, it's just because uh, you don't cut up the stair, do you? That's the length of the stair.
Okay, so but
Right.
if we find the value of x dash using this way, would it be 2, the answer?
No, let's see. Let's understand the observer can be the problem here. This one here. Oh, sorry. I make mistake here. I made mistake here. Sorry. I was thinking the top of the ladder is leaning against the wall. This situation is leaning against the wall. Do you see what I mean? See the difference? Leaning in this one is top extending over the wall. So extending over the wall means that the picture should be like this. There we go. This is 18. This is 12. This is X. So Y is always 12. See the picture?
Yeah.
The difference? Okay. So what we computed earlier, that is the leading part, these situations. Let me write down the situations. That's the situations. Okay. But now let's compute this one. We're done with this. Okay. Now let's do the situations where the ladder let's over the wall. So what's the term? Top extending over leaning, but top extending over the wall. Okay. So let's see. Okay. So now the situation is like this. All right, but that's good then because we can compare what's there. So this is 18. Okay, but this is 12. So this is x. And what is known is the x dt is 2. Okay, so the question is that uh, vertical velocity of the top end. Um, okay, vertical velocity, right? So let's picture. So when you pull this to the right, so somehow this will let's see. This is going down like this. Okay. So we need to find this speed here. Okay. But the thing here, this is quite the tricky part is that this is the picture. There. You have two triangles, right? So the whole thing is 18. Okay, this is you have x here, you have 12 here, and then you don't know, you got to figure out what is this one. Okay, and dx dt is 2. The question is that, say this is s. Okay, so the question is what is the s dt equals to? Okay, when say this one alpha is 60 degrees. Okay. All right. So let's find the relation here. Because this is also alpha. Okay. So we need to rate a change of that alpha. All right. So how to find a relation between s, x, and that's 18. Okay. Let's see how to find it out. Any idea? It's more elaborate because you have 2 or 3 even triangles here. Okay, so, or you can draw this by this one. Say this is S R, say. So this is all this is 18. This is 12 plus S. Okay. So if you know this is 12 plus S, then you can compute this one. That is 18 minus there we go. Okay. Okay, so you need to, this is the relations, this length, and this length is move to the 2 here. Okay, okay, there. It's yeah. Okay. Do you see see the picture here? So this is the X. This is X bar. Okay. So to say this is X bar square is there. Okay. So then as usual, do implicit differentiations. So you get 0x, this is 0. This is negative. So S prime plus 12. Sorry. 1 because the chain rule. F there. All right. So what is the questions? The question is about this one. Right? So we need to find this data here. We know X X bar. Oh, this is 2. Right? Because the X or X is this the same. This is 2. We got to find this one when this is now the instantaneous picture here. When this is 60 degrees. This is 18. So you know what's the length of this. So 18 cosine 60. Cosine 60 1/2. So this is 9. The whole thing is 9. Okay, so this we know this one. we need to find S. Okay, but how to find S? How to find this one? Well, we know what is the height for the whole thing. The height is the 18 sine 60 degrees. Okay, sine 60 degrees, this is 12, so subtract 12, so you get S. Or if you notice, what is S? S plus 12. S plus 12 is the height for the whole thing. The height for the whole thing is cosine, sorry. Okay, so you get also this one. So you can find this S prime. Okay, so that's how you do this one. I'll let you finish the computations. Yes. Okay. So you know this data here. Then you can compute. When alpha equals 60 degrees. There. Okay. So it's how you slightly more complicated in this the picture. All right, so you have those two cases, leaning against a wall and not leaning, over the wall. Questions?
No questions.
All right, then let's go to this one. What's the differential and approximations? Okay, so this is the last thing of this chapter. So, all right, so this is how you quantify an approximations. All right, so let's I'll tell you about the little bit history of the calculus. Uh, Mostly the study of calculus really rests on the two big person of the calculus, legend of calculus, that is Newton and Leibniz. Newton's in Cambridge, in UK, and Leibniz at the time in, I don't know where is it. I don't remember what is Leipzig. I think Leipzig in Germany. Okay, so around the same time, 1680 something to early 1700. Okay, so eight, three, and okay. Now um, the calculus developed by Newton and Leibniz, they are quite separate. I mean, they developed the calculus independently. It is their schools, their disciples that disagrees and then have a conflict, right? So about who invented calculus. Okay, but they both, and at the time, because of course, the transportation is not that easy, and Newton and Leibniz never met actually. They have the separate calculus. All right. So the thing is, they have a different notation for differential. Derivative. Newton used a dot or prime. As you see in physics. So V is the F dot, S dot. A acceleration is S dot dot. So, or while Leibniz use this one. The X of F, something like this. Okay. So in a sense, the later on you'll see that the Leibniz notation is more convenient because it's more informative. Um, it points out what the variable, what is variable, what is the functions. Okay, so this is Leibniz notations. Okay, as delta x goes to 0. Okay, so in the Leibniz notation, this is a really a intuitive. Okay, so when you have delta y over the delta x, okay, so this converge, take limit to dy over dx. Okay, so delta becomes d. Okay, so this is the intuition. It's far more intuitive than this just dot or prime notations. Okay, so this is limit. All right, the idea is that this delta is a ratio between difference in y and difference in x. Okay, so it's a ratio differences. Okay, but the dx, but dy dx is not necessarily a ratio. Okay, so how to make sense of this? Ratios, but limiting to a non-ratio. How to make sense of non-ratio. Okay, so example here. If I let me- okay, so for example, if I write down something like this, so 3 31 over 10, 314 over 100, 141 over 1,000. 10. Okay. Can you guess what I'm writing to actually?
Pi.
Pi, right? So this is just a pi because this is actually just 3.1, 3.14, 1. See, this is in decimal, but actually This is ratio because 3.1 is 31 over 10. This 3.14 is 314 divided by 100. Okay, so all these are ratios. So this is a sequence of ratios. But this we know, well, we foresee this is going to pi, while we know that pi is not a ratio. Pi is not rational number, not a rational number. Okay, so this is how to make sense of ratios limiting to a non-ratio. This is example. All right. So the thing is, so df dx, even though we write something like this, is not a, it is not a ratio. Okay. So that's just a little bit history, background of to these notations, Leibniz and Newton's notations. Okay. Now we really would like to make sense of this how to make sense dy dx as ratio. So that's equations. Right? Even though it is not. All right, so let's just force to do this one. Okay. All right, so let's see here. So let's define the x is really the delta x. Okay, and what is dy? dy is times this is called differential of x. This is differential of y. Okay, so if we have this, then let's see what happens here. So we can just compute now dy over dx, really. Okay, so this is just a ratio now, what you get here. So this is just but because this is equal to dx, that is that's what you get, derivative. Okay, so now we know this as ratio dy over dx is a ratio of a differential. So now dy over dx is a ratio of differential. Okay, so how we see this one? Okay, let's do this one. Example. See, let's go back to the next book. Okay. Okay, so what does it mean? Okay, pictorially, what it means is that so in the beginning, that is the limit of okay. So when delta x is small, okay, so that's dy over dx is close to okay. So what we find is that so dy is close to uh, so what we have dy is approximate delta y. Okay, this is an approximations. All right, so let's find out the meaning of this one. Okay, here we go. Okay, for example, this is the graph. Okay, so this is x1. X2 here. Okay, and here we have y1. This is the y2. All right, so let's see here. This is what we call delta x difference. Okay, and this is what we call delta y difference. Okay, so what is that the um, let's draw the tangent line at x1. Okay. All right, so let's see here. So when we compute this one, so this is slope. Slope is dy f prime. So just okay. So what is when you uh, slope times difference? What's this? Slope times this one. What you get? This is tangent line. Okay. So when you multiply slope by this difference, x difference, you get y difference. So that's why this is the delta. Sorry, not to say that delta. Okay, this is this difference. In height. So this is what you get. This is our dy. Okay, so when you make this approximation, you're comparing dy in comparison to that's delta, the real difference. Difference. This is differential. Okay. So what you find later is that the dy approximate so here y1 you can approximate using 3 to y2. This is just y1. Y2 moves here, y1 plus dy. What is this one? Plus okay. All right, just one example. Let's do approximations. Say square root of something like say 101. What can you say about the number? About the approximations? Close to what? What you expect? What do you expect? What is this square root of 101?
Zero,
Why 0?
because there is no term of x or y, because it's a coefficient.
No, square root of 101.
Around
Forget calculus.
10.
around 10,
Around 10. Okay, bigger than 10 or smaller than 10?
bigger.
Slightly bigger, yes. All right, so we'll try to make sense of that slightly, the word slightly bigger. Okay, so let's do this one. Let's formulate it. All right, so think about problem of square root, the functions. And think about something that's easy. Say a equals 100. Okay. So we know that f of a, that's easy. Okay. But our x is now is not x is our 1. So this is actually that's 100 plus, well, we count that 1 as that our delta a or error. All right, so this is x error. Okay. So we need to find find delta y, or if that yet do approximations. Okay, so get this one here. So is approximated by dy, well, we can compute dy as f prime of x computed at A times delta X. Okay, so how to do this one? Well, that's easy because we now have the functions. Derivative is 1/2 square root of X. Okay, and you plugged in that's A equals 100, right? So you get that's 100, 120 times delta X is just 1. Okay. So now what's our difference? So now square root of 101 is approximately 10 plus or minus.
Plus.
So 1/20 is, let's see, what is that? 0.5, right? So now you can check your calculator. Square root of 101. So use that thing. Calculator gives you 5, 6. Okay, so that's how you do this kind of approximations. Can you see this? You can compare this.
Sir, I'm still slightly confused on how you got 1/20 as the delta X value.
Plugged in 100.
Yeah, how do you get 1/2 root X? How do you get from there? to there?
What is this?
Uh, all right, okay.
Okay. All right.
Okay, thank you, sir.
Let's take a break for 5 minutes.